Finding NeMo focuses on mitigating memorization in diffusion models. Why is that a thing? Like in the last couple of years, basically, we saw a vast rise in terms of diffusion power. So we now have these diffusion models that enable us to generate extremely high quality content. We can generate images that are rich in detail and that have very, very clean and clear styles. But there is another thing about that, which is that diffusion models are actually known to output their training data at inference time. What that means is basically, if a diffusion model is trained on your data, basically on an image of your face, for example, if you then basically prompt the model to generate you, like for example, inserting your name and new image, it might output exactly the same image of your face. And that has multiple problems. I think the first problem is rather obvious. It is a privacy problem, because probably you do not want anybody on Earth being able to generate your face exactly like on your image. And the second problem is a problem of intellectual property. So it goes actually beyond individuals, but you can imagine that artists generate their images, and of course they want recompensation for that. And now the diffusion model is able to actually one-on-one copy their images if it was trained on them. So that is of course a severe issue, and we really need to mitigate it. What has been done in the past focuses mainly on two different types of defenses to prevent the memorization. The first type was about retraining the model. So what you basically have to do is you train your whole diffusion model from scratch, and then you just generate a lot of images. You identify which images are basically regenerated, and so they must be memorized. Then you remove them from the training set and you train from scratch. As you can imagine, this is a super costly venture, because training like one run of the diffusion model already is a very high costly thing. And then we are not even sure that they are no more memorized samples, because we know that the samples that were previously memorized are no more memorized. But how about new samples? They might still be memorized. So actually this type of defense does not give us any guarantees about that. The second type of defense that people tried mainly focused on inference. So during the diffusion process, they kind of tampered with the model. So for example, like the diffusion models that we're looking at today are text-guided diffusion models, where you give a text prompt and then the model generates you an image according to that. And what people found is that actually if you get the text embedding, which the image is trained on, and then for every iteration step you kind of noise this text embedding, then you will prevent the memorization. You can also have the same effect by scaling the attentions, but this is inference time, so you need to do it at every diffusion step. And the problem with that is it only works if your model is basically behind the black box API. But at the moment that you release your model to the public and people can actually directly interact with this, these kind of defenses will not work anymore. And that was basically the departure ground for our work, where we said we want a defense that alters the model directly, such that the memorization is permanently removed from it. But we wanted that to be cheap in terms of computation and like not very time consuming. And our intuition on why we, or like how we can do that is by identifying which of the model parameters are responsible for memorizing particular data points. And our intuition here, how we can identify neurons that memorize data points, is that if a neuron has a very strange activation, mainly much higher activation on one particular input data point than on any other data point, this neuron is most likely responsible for memorizing that data point. So let me walk you through how we can identify such neurons. And therefore, we will start at the short excursion basically on the background of diffusion models. So what diffusion models do in the core is that you give them some random noise and put actually a text prompt such that it knows what to generate, and then the model denoises this noise to generate you an output image. How can the model do that? It basically during training is provided with some training image that we add noise to. And then at every step, basically, the model needs to predict some noise, and which is things that was added to the image. And our loss function is then the difference between the originally added noise and the predicted noise. Thereby, the model becomes significantly better in just predicting you what noise was added. And then at inference time, if you start with a fully noised image and you give it a prompt, then it will like predict you some noise, and then in multiple steps you always subtract that noise, and you more and more resemble your original like images, or you more and more resemble like proper natural images that you can then generate. So what we now want to do is to find out memorization. But there is a caveat, because if you want to find memorized data points, comparing that in the pixel space is extremely expensive, and that is because every diffusion generation takes multiple denoising steps. So it can take you per image a few minutes on a GPU to actually generate an image. So of course, if we like for every image like generate images and then like we compare them, it becomes too costly and we cannot do that. But luckily there is some insight that prior work gave us, which is that you can like differentiate between memorized and non-memorized samples already in the first denoising step. Because what's the intuition is that if you have a non-memorized sample, if you give different random noise as an input seed, it will at every time give you a different denoising trajectory. It's kind of intuitive, like why would it like give something similar? But the thing is, with memorized samples, if you give different input noises, it will still always kind of choose the same denoising trajectory, because it like overfits that image. It always like pushes you towards going back to that train image. So the consistency between like the first noise prediction is much, much higher for memorized samples. And in comparison to generating the images like fully from scratch, taking just the first step is of course extremely computationally expensive. So to basically show you how that looks like in practice, if we compare like the final generation on the memorized prompts and then the first denoising step, you can see like no matter, like we have 4 different random seeds here, and they all have kind of the same noise. Whereas for non-memorized prompts, it's always a very different noise. So we can pretty easily tell them apart from one another. So how we can eventually quantify that is with the SSIM score. And the SSIM score is a structural similarity index. It compares basically low-level features and structures, and it allows us basically to compare the noise differences for non-memorized and for memorized samples. So if we like look at that just empirically to verify that it really holds in practice, we can compare like how this SSIM score differs between non-memorized and memorized data points. And indeed, you can see that for the non-memorized points, this SSIM score is significantly lower than for the memorized points. And what we distinguish here is the like memorization in 2 forms. The first one is template memorization, and what you can see in template memorization is about the model outputting like one like particular element from the image. Like here, for example, it just stole this carpet from the original image and outputs that. And the second form of memorization is the verbatim memorization, which means that the model copies one-to-one its training image. And now let's dive into basically the core of our method, namely detecting when a neuron memorizes. And therefore, we calculate the Z-score. So like a Z-score is a very simple statistic that basically compares a data point to a distribution and finds out how much an outlier this data point would be. And we use this to like quantify the activation of a neuron versus like standard. So what we do is, like we look into every layer and every neuron, and in our work, because they have shown to be most responsible for memorization, we look into the cross-attention layers, and then basically we infer a prompt which we want to like find whether it's memorized or not. And then we compare the activation of this particular prompt with a mean activation on a holdout set and like the standard deviation on a holdout set. And for this, basically, like having these standard activations is just a one-time operation where we take basically 500 validation samples, we infer them through the model once, we capture how they activate the neurons, and then basically for every neuron now we have that score, and like for every new prompt, we can just compare it against the score. So eventually we'll find out how much of an outlier behavior does any particular neuron have on any particular data point. And just to also quantify that, we just presented that here in terms of this like Z-score that I just showed you. And what you can see is that it differs vastly between memorized and non-memorized data points. So for the non-memorized data points, the Z-score is always around 0, which means that they have relatively like inlier activations, so they are actually like normal. But what we see for the memorized sample is that they have a very wide variation. So what it means is actually they have kind of an outlier behavior. And this way we can then detect like if these neurons are responsible for the memorization here. But now we need to like really tie it down and get to a small set of neurons. And therefore, like we think about like what neurons to select actually for memorization. And we start off with an initial threshold, which we then later refine, but we start off with an initial threshold and say that every neuron on the given data point that has an activation or that has a Z-score higher than that threshold gets first into a candidate set. So we start with a relatively coarse-grained candidate set where we put all the neurons that have a higher Z-score on the sample than the threshold. And that gives us the candidates. And like, then we also add the neurons with the top K highest activation because we found that often they are also involved in memorization. And what we now do is in a single step, we zero out all of these neurons. And then we compare how does memorization change between the non-zeroed out version and the zero out version. If memorization is basically mitigated, then we know that we have a good initial candidate set. If memorization does not decrease yet, what we do is we like go down with our threshold. So that means like the lower the threshold is, the more neurons are included in the possible candidate set. So now we have more neurons in the candidate set, and we do the same thing again. So we zero all of them out. We see how does it affect memorization. Does it stay the same or does it go significantly down? If it goes significantly down, we are there, and we have our candidate set. Now the problem is that the candidate set is still relatively large. It's like, it can be even up to 100 neurons. And of course, if we were to zero out all of them, we would just harm the performance of our diffusion model. So what we now do is a refinement step, where we basically want to find out which of these neurons really now form the core set of our memorizers. And how we do that is basically, we have all these neurons zeroed out, and then layer by layer we go and we basically switch them back on. And we see like how does it affect memorization? Does memorization go up again, or like does it stay low? If it goes up again, then of course these neurons must be in the set of memorizing neurons. So like then we go neuron by neuron inside that layer, and we do that basically for all the layers until we have a set of neurons that are responsible for the memorization. And what was actually very interesting for us to see is that NeMo effectively mitigates memorization and also makes more diverse generations. What we looked into is the SSCD score. Like SSCD is also a standard computer vision score that basically detects image copying. So if you have a SSCD score of 1, it means basically your image is like 1-to-1 copied. And you see that for the memorized data points that we have, if we do not deactivate any neuron, they are copied, like exactly. We also look at the alignment score in terms of CLIP, which means like how well does the generated image align with the prompt that we provided. Because it would be a shame if we like switch off memorization, but then also have an image which looks totally different than what we actually want. So we need to also keep the alignment high. And then we compare NeMo basically against the random baseline. So like switching off 4 random neurons versus switching off 4 like NeMo identified neurons. And if we switch off the random neurons, what we see is that memorization is hardly affected, basically. So it stays nearly 1, whereas for NeMo, memorization goes down nearly to 0. And then looking at the alignment, while we switch out the NeMo neurons, we still get a very good alignment in our generated images. So we can say that basically the performance is not very much affected. What we also looked into is like what it qualitatively means to deactivate these neurons. And basically we started off again like generating from 2 different seeds. We already heard that like if we have memorized samples on 2 different seeds, we will generate the same image. And that is basically what happens before we apply NeMo. But now that we block the neurons according to NeMo, what we can see is basically the generation still gives us the correct concept. It's still obviously the same woman, but we do not get the memorized input image anymore. And what you can see here in the middle is the number of neurons that we had to zero out for that. Like looking into a few more examples, actually, we can see that in many cases, it's very much enough to zero out a very small number of neurons, like 1 or 3, to basically move from the point where we output 1-to-1 the training image to the point where we generate diverse data. And like to just have it more quantified, we just looked over all the 500 memorized prompts that we have. And we looked how many of the, how many neurons does each of them need to be completely unmemorized. And what we see is that especially for verbatim memorization, it's usually less than a handful of neurons that are memorizing this particular data point. And for us, this was a very surprising finding, given the complexity of the diffusion models and given the complexity of the images that they are trained on and that they generate, finding out that only one neuron is responsible for the memorization of a data point, it was really, really interesting. What we also found, and that was even more interesting for us, was that some neurons seem to be purely memorizers. So basically they are neurons that memorize multiple of the data points. So for example, this neuron 25 here, I think it memorizes between 20 and 30 different data points out of our 500 prompts. And if we block this one particular neuron, then memorization for all of them is gone at the same time. And just by looking into that a bit more qualitatively, we found that often this, the same memorized things basically are from the same concept. And here, for example, I would say the concept is people. So this neuron is apparently only responsible for memorizing people. The last thing that we then had to check is how does NeMo affect our overall generation quality? So we looked at the quality of the generated images from the memorized prompts, but now of course we want to know how does the model behave overall. And there are multiple scores how you can assess the generation and diffusion models. One popular is the FID or the KID score. Basically a lower score means that the image generation is better. And here we plot basically on the x-axis how many neurons we zeroed out, and on the y-axis the performance. And what you can see is that for the longest time, basically the generation quality of the model does not drop. Only when we reach around 500 blocked neurons, then we can see that the quality slightly degrades, but it still stays also even in the standard deviation. So overall, what we could see from here is that while it mitigates memorization, our method hardly affects the performance. So to wrap all of that up, we can see that NeMo allows us to memorize individual data points in individual neurons or parameters of the diffusion models. And that if we deactivate these neurons, we do not only mitigate memorization, but we also preserve performance of the model. And with that, I'd like to finish, and I'm happy to take any questions.